All right, welcome back to our second lecture, second round of lectures, that is for this week. And we're going to resume our discussion of mechanical vibrations and take the next step forward in completing our discussion so that we know exactly how to compute these and set up the differential equations required to solve situations like these. So let's go ahead and take a step back and recall a couple things. First of all, I want you to recall what we obtained last time when we derived the spring equation or the mechanical vibration equation using Newton's second law. It said m times u double prime. Um, okay, sorry about that. Just had a little glitch with the pen. Okay, and what is this? So mu double prime is the force due to gravity, or mass times acceleration, right? And acceleration is the second derivative. And what we added this to was a constant called gamma multiplied by u prime. And this referred to the damping forces that are associated with our mechanical vibrations. And then this was added to some constant k times u, and this referred to the force that's exerted by the spring itself that's used in our model. And all of this is equal to the external forces that are outside of the system. Okay? And there was a couple of initial conditions that we had that went along with this. The first one was u of 0 equals u naught. And this referred to the initial displacement from the equilibrium position. Okay? From the equilibrium position, or POS for short. Okay? And the other initial condition we had was u prime of 0, which equals u prime sub 0, and this referred to the initial velocity. All right, so that's where we ended last time from our discussion. And so today, what we're going to talk about are a few different scenarios that is associated with the equation that you see above. The first scenario refers to free, or what is known as free, undamped vibrations. Okay, so this will be the first case that we're going to work with. And it's usually considered to be the simplest case that we can consider. So what does this mean? So free, or what's also known as unforced vibrations, means the following. So free, the word free in this case, implies that the external forces felt by the mechanical vibrating system are set equal to 0. Okay? And undamped vibrations means, and you probably could guess, that undamped implies that the constant gamma is set equal to 0. Okay? So that's what free undamped vibrations refers to, where we have capital F of t set equal to 0, and gamma, the constant, set equal to 0. Okay? So the equation that we have up above at the very top, this main equation up here, then becomes the following. Becomes m times u double prime plus k times u, and that all equals 0. And that's a much simpler differential equation to work through and to solve. Okay? And so that's what we're going to do now. It's very easy to solve this in general, and the way we go about it is by using the characteristic equation. And after applying the characteristic equation, after applying the characteristic, oh, ran out of space here. So characteristic equation. Okay, so after applying the characteristic equation, we obtain the roots. We obtain the following roots. Okay, and that is going to be r, the roots, and they're set equal to plus minus I times the square root of k divided by m. Okay, and that's going to be a very important result that we're going to see many times, especially in your examples and in other problems and other scenarios that we will work through using mechanical vibrations. Okay, so there's a way to rewrite this expression. Normally it's rewritten in the following way. We say, excuse me, we normally say that r is equal to plus minus omega naught times I. No, it looks like W. So this is generally referred to as little omega. And so W naught is set equal to the root that we have above. So little omega naught is set equal to the square root of k over m. Okay, so that's typical, and we'll see that again and again and again. And so there is a name for this. Little omega naught is referred to as the natural frequency, or is called the natural frequency. Natural, there we go. Natural frequency. I'll just abbreviate. Okay. And also, you're going to see this again and again as well. If, and this is just a property that we can observe, if m is bigger than 0 and k is bigger than 0, that is to say they're both positive, we can always guarantee or say this quantity will not be complex. That is, it'll have real answers only. Okay, so I'm going to go ahead and stop here for this first part of our first video for this lecture, and then in the next lecture we'll take the next necessary steps forward. Stay tuned.